All right, we'll go ahead and move to our next speaker. This is a recorded talk. We will have a presentation by Pengcheng Zhu, who is also from ETH Zurich, on FPsPIN, an FPGA-based open hardware research platform for processing in the network. And if you have questions, please send them directly to the author. Thank you.
Hello everyone, I am excited to be here at Hot Internet Connects to talk about our recent work on FPsPIN. Let's get started. As we know, networking in HPC is working with higher and higher data rates. The CPU architecture, however, hasn't changed much. It takes around 10 nanoseconds to access a single 64-byte cache line. Sent over the latest 400 gigabits per second host adapters, this 64-byte cache line will only have a time budget of around 1.28 nanoseconds. This is especially problematic for workloads like data transformation and protocol processing. As a result, offloading lightweight data processing to the NIC itself is gaining popularity. However, these solutions have yet to see wide adoption in high-performance computing. One main issue with existing commercial solutions is that the programming model they offer are mostly vendor and hardware dependent. This results in high cost and low adoption. In contrary, the SPIN project from ETH Zurich offers a hardware agnostic programming model for in-network processing. The model aims to enable wide adoption for NIC offloading across the broad HPC community. Now, let's take a closer look at SPIN. SPIN stands for Streaming Processing in the Network. At its core, SPIN defines an abstract machine model for on-path smart NICs. It defines packet handlers. These are small programs that get invoked on packets and messages. There are three types of handlers. Header handlers are invoked at the beginning of a message. Packet handlers are invoked at every packet of a message. And tail handlers are invoked at the end of a message. These handlers run on handler processing units, also known as HPUs. The handler functions access packet data in fast local memory. It talks to the host CPU through DMA to host memory. Now, as we have seen, since SPIN is an abstract machine model, it doesn't actually define the exact ISA, that is instruction set architecture of the HPU. Neither does it define the actual underlying network. Now that we have this abstract machine model, we need an implementation of it. FPsPIN implements SPIN with the Pulp RISC-V cores as HPU. This is implemented in RTL, which means which makes it ready for ASIC tape-out. In addition, it has also implemented global and local schedulers for handlers. And it defines a hierarchical memory system to implement the SPIN handler programming model. However, with that said, FPsPIN still lacks a couple important components to become a full system. The network and host interfaces were not implemented in hardware, but only simulated in software. Rated the kilohertz clock speed. This makes evaluating complex handler programs very impractical. With the background set, now we can talk about our contribution to the SPIN project in this work. We integrate FPsPIN with a NIC to implement the missing network and host interfaces. We use Corundum, an open source FPGA-based NIC. Corundum also offers DMA access to host memory, so it provides everything we need. To bridge Corundum to FPsPIN, we need to implement several adapter modules to convert interfaces and generate descriptors. Among them, The matching engine decides whether a packet gets sent to FPsPIN for offload processing, or it can continue in the normal NIC data path and gets delivered to the host CPU. The HER generator, the handler execution request generator, pulls together a descriptor for the FPsPIN schedulers to launch a handler function on a specific HPU. There are also various DMA modules that convert between streaming and memory interfaces. For a detailed description of each adapter's functionality, please refer to the paper. Now, just the hardware alone is not enough for a full system. The software is divided into two parts, the NIC software and the host software. The NIC side software runtime for the HPUs are largely unchanged compared to FPsPIN. As recap, the handlers are C functions. They get pointers to packet data in the local SRAM. You can see an example of a handler function implementing a UDP ping pong server on the right-hand side. The handler function manipulates protocol headers in place in SRAM to generate a response packet. It then invokes the SPIN API to send the response packet back into the network. While we didn't have to change much of the SPIN runtime, host-side software simply didn't exist before. On the right-hand side of the screen, you can see the routine to program the ICMP ping pong example to the FPGA. The most important bits to program are the matching engine to to only match ICMP packets. This is the rule set function at the top. It matches against different parts of the headers to decide if the packet is a ICMP echo message or if it is not, in which case the packet should then go to the CPU. The runtime also sets up a DMA page for communication between the NIC and the CPU. We evaluate our implementation on an AMD server with a Xilinx FPGA. As you can see on the right-hand side, this is a tower CPU setup, and we use a FPGA add-in card that talks to the CPU over PCIe. The two Ethernet ports on the FPGA board are attached via a DAC, directly attached copper loopback cable. As you can see, the overall test setup is easy to assemble and very cost-friendly. For the experiments, we present latency, throughput, and overlap ratio results for our implementation. I will soon explain what overlap ratio actually is. For time reasons, we can't fit all experiments into this talk. Please refer to the paper for other experiments. We evaluate latency of running handlers through ping-pong benchmarks over ICMP and UDP. With FPsPIN, 3 operation modes are possible. Host mode bypasses the FPsPIN cluster, that is the HPU cluster. This is bypassed completely, and in this case, FPsPIN works as a normal Ethernet NIC. Host plus FPsPIN passes the packets through the HPU cluster, but the host CPU is in charge of updating the checksum and manipulating the header fields. In FPsPIN mode, the HPU cluster generates the response. That means the HPU cluster is responsible for manipulating the header fields and calculating the checksum. The host CPU is not involved at all. We see that in UDP, both FPsPIN modes perform consistently better than the host-only mode. This is due to the high overhead in context switching in the Linux UDP stack. Now, for ICMP, we see that the latency linearly correlates to the payload size. This is due to the protocol checksumming the entire payload, making the protocol processing relatively heavyweight. We can see that FPsPIN starts out better than host-only mode, but gradually loses the latency advantage as payload size increases. This shows that how the HPUs run slower than the host CPU, since they are on the FPGA running at a lower latency. Another factor to take into consideration is that the ICMP stack on Linux is implemented in kernel, so it has naturally lower overhead. The second experiment demonstrates the ability of FPsPIN to overlap communication on the CPU with computation on the CPU with communication on the NIC. MPI data type transforms are a class of data transformation between a logical data structure in memory to its wire representation to send over the network. Conceptually, it is a form of serialization-deserialization protocol. We evaluate two data types, as you can see on the top. A simple data type, this simple data type is just an array of floating point numbers. On the bottom, the complex data type stacks floating point numbers in multiple layers with nested and overlapping structures. These two data types highlight different amounts of workload to carry out on the NIC. We implement both of these data types with the MPI-CH data loop compiler on CPU. With the MPI-CH data loop compiler. The implementation on the CPU is the reference implementation for MPI-CH. And the same implementation is ported to FPsPIN to run on the RISC-V architecture of the HPU. Oh, sorry. We overlap matrix multiplication on the CPU with MPI data types transformation on FPsPIN. And we calculate the overlap ratio as time spent in matrix multiplication, that is the computation work, over the total time spent by the CPU, that is computation plus communication. A 100% overlap ratio would demonstrate free communication thanks to offloading. And now, before I show you the results, I would like to note that this evaluation was not possible before on FPsPIN due to the host interface not being implemented at all. The results look like the following. So we see that for longer messages, we achieve our over 98% overlap. This means that we get the MPI data types processing almost for free since we are offloading them to FPsPIN. This frees up more CPU cycles to perform useful computation, in this case matrix multiplication. We note that shorter messages will result in a lower overlap ratio. This is due to increased polling overhead on the whole CPU. Conversely, a more complicated data type will reduce the need to poll, thus increasing the overlap ratio. We also note that the FPsPIN implementation has lower throughput compared to the CPU implementation. This is to be expected since the MPI-CH version is highly optimized for server CPUs, while the FPsPIN implementation was simply ported as a demonstration. The whole CPU is also running at a way higher clock frequency and has a more complicated microarchitecture compared to the PULP RISC-V CPU core. I have just presented to you FPsPIN, a SmartNIC research platform that implements the SPIN abstract machine model on FPGAs. This work enables full system evaluation of NIC offloading for HPC applications. The system is fully open source on GitHub for you to try out. And with that, back to the host.